Hello everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss some analytical problems based on PN junction diode. In the few lectures, we have discussed about semiconductor devices, and to understand the concept very clearly, it is always good to solve some analytical problems. So, before starting doing the problems, let us look at the formulae on which we are going to do the numericals. So the first one is I is equal to Is exponential EV by KT minus 1. So I here represents the current flowing through the diode. I is the current that is flowing through the diode. And Is represents the saturation current. E here is the charge of electron. Which is constant 1.6 into 10 power minus 19 coulombs. V is the voltage applied, due to which we are getting the current. So applied voltage. And K is the Boltzmann constant. K is the Boltzmann constant. As it is a constant, its value is 1.38 into 10 to the power of minus 23 joules per Kelvin. And T here represents the temperature. So as you have seen, all the quantities we express in the SI system. So the temperature also has to be expressed always in degree Kelvin. Even if it is given in other units like Celsius, you will have to convert it into degree Kelvin. And one more thing we have here is beta, or in some books it may be written as eta. Beta here represents the ideality factor. Beta represents the ideality factor. Actually, if the ideality factor beta is equal to 1, we generalize it and write it as Is into exponential EV by KT minus 1. But if the value of beta is given, then we'll have to write its value. And this value ranges between 1 to 2. Generally, 1 for silicon and, 1 for germanium and 2 for silicon. The range 1 to 2 is the range of this value. And in some problems, if the value of beta is not given, that is the ideality factor is not mentioned, we take it as 1. So in the numericals, what we are going to do is, given the values of Is and the voltage, the saturation current and the voltage at a given temperature, we can very easily calculate the current flowing through the circuit. Or if you are given I, you can also calculate the Is, that is the saturation current. We are going to do numericals on calculating first the current flowing through the circuit, then the saturation current, then also we are going to find the voltage or the temperature. So this is the main formula that we are going to use to calculate the current or the saturation current or the applied voltage or the temperature at which we are getting the saturation current. So we'll be using the same formula. And in some cases, when the thermal voltage is given, the formula for thermal voltage. Thermal voltage Vt is given by Kt upon E. Kt upon E is the thermal voltage. So I can also modify this formula and write it as, if the thermal voltage is given, I can also write it as I is equal to Is exponential V by beta Vt. This is Vt minus 1. So is it clear? So instead of Kt by E, we are going to substitute Vt, where Vt represents the thermal voltage. Okay, with this we will move ahead to do the numericals. So the first question is, calculate the value of applied forward voltage for a PN junction diode if Is, the saturation current, is 50 microampere and the current flowing through the circuit is 2 ampere and the value of E by Kt is 40. What we have to calculate and what is given, we will write very clearly in the data given. So what is the data given? First, the saturation current Is is given 50 microampere and then the current flowing through the circuit is given 2 ampere and the value of E by Kt, because E and K are constants, T is the temperature. Instead of giving the temperature, they have given us the value of E by Kt, which is equal to 40. And what we have to find here is the applied forward voltage we have to find. So V is equal to how much? This is the first step. Whenever we are doing analytical problem, the first thing is to identify the data given. So we have identified the data given and what we have to find. Next comes the formula. What is the formula that we are going to use to do the numerical? So I is equal to I naught exponential EV by Kt minus 1. So let us now substitute the values, but before substitution, let us see whether all the given quantities are in the same system or not. Here, the current is Is, the saturation current is given in microampere. So we need to convert it into ampere, 50 into 10 power minus 6 ampere. The saturation current, we have converted it into ampere. And now what we are going to do is the substitution, substituting all the values in the given formula. So I is 2 ampere is equal to I naught. I naught or Is both mean the saturation current only. So in some books they follow the notation I naught for saturation current. In some books they follow Is, which is nothing but saturation current. There is no confusion about it. I naught or Is represents the saturation current. So I naught, that is given as 50 into 10 power minus 6 into exponential E by Kt value is given. The value of E by Kt is 40. So we have 40 volt V minus 1. So we have done the substitution. And what we have to find now is the voltage. We have to find the voltage, that is V here. So let us find out V from this expression. What we are going to do is, I'll take all the values onto this side into 10 power minus 6 will be equal to exponential 40 volts minus 1. So if I take this to the numerator, I can simply write it as 2 into 10 power 6 by 50. And this minus 1, if it comes on to the other side, it will be plus 1. and this will be equal to exponential of 40V. So because we have to find V, the voltage, I'll take logarithm on both sides. Taking log on both sides. So what we'll have here is ln 2 into 10 power 6 by 50 plus 1 will be equal to 40V. And if I simplify the value inside the bracket, I get ln 4 zeros 1 is equal to 40 volt. Now, you can use your calculator to find the value of ln 4,01,000. You can find out this value using the logarithm book, or you can use your calculator to find this value. And this value we are getting it as 10.5966 is equal to 40 volts. So therefore, V will be equal to what? 10.5966 upon 40. So we get 0.256 volts. So what is the voltage we are getting? 0.256 volts. So this is the voltage at which we are getting the saturation current as 50 microampere and the current flowing through the circuit is 2 ampere. Now let us move on to the second problem. The current in a PN junction at 27 degrees Celsius is 0.18 microampere when a large reverse bias voltage is applied. Estimate the current when a forward bias of 0.98 volt is applied. So let us write the data. What is the data that is given and what we have to find? When we write it clearly, so the concept becomes very clear. So first given is the temperature. Temperature given is 27 degrees Celsius. And the current that is flowing is 0.18 microampere for a large current. So this is the saturation current, 0.18 microampere, and the forward voltage is 0.98 volts. We have to estimate the current. I is equal to how much? So this is the data given. Now again, we need to first check the unit size set. So we need to do some conversions here. 27 degrees Celsius, we will convert it into Kelvin. So what is the conversion? 27 plus 273. So this is 300 Kelvin. So the temperature here is 300 Kelvin. And what is the saturation current? 0.18 microampere. So I'll convert it into ampere. So 0.18 into 10 power minus 6 ampere. So this is the current. Now what is the formula we are going to use? The formula which we have already discussed, I is equal to Is into exponential EV by kT minus 1. So this is the formula we are going to use. I we have to find. What is Is here? Substitute the value of Is, 0.18 into 10 power minus 6 exponential E. E here is the charge of the electron. It is a constant. 1.6 into 10 power minus 19 coulomb. and Boltzmann constant K is also a constant. You need to remember these values. I'm not going to write it again and again. We'll substitute it directly. Minus 23 joules per Kelvin. So let us put the values for E, V and KT. So 1.6 into 10 power minus 19. And what is the voltage applied that is given? 0.98 upon the value of K. 1.38 into 10 power minus 23 into temperature. We have converted it into Kelvin, 300 Kelvin. And one more thing we forgot here is the ideality factor beta. So I said whenever beta is not mentioned, we consider it to be 1. So we have taken beta to be equal to 1. Minus 1 we have. So if we simplify, I is equal to 0.18 into 10 power minus 6 into exponential. What is the value we get when we do this using calculator? You will get 37.87 minus 1. So you can also get the value of the exponential 37.87 and subtract minus 1 and multiply it with 0.18 into 10 power minus 6. So you will get I will be equal to 5.03 into 10 power 9 ampere. So this simplification you can do using the calculator, and also this value you can find using calculator. Subtract 1 and then multiply it with 0.18 into 10 power minus 6. You get I to be equal to 5.03 into 10 power 9 ampere. Now we'll do the third problem. Evaluate the forward bias current of a germanium diode when forward bias voltage of 0.4 volt is applied and the reverse saturation current is 1.17 into 10 power minus 9 ampere and the thermal voltage is 25.2 millivolt. So what are the values given? Applied voltage is given, the saturation current is given and the thermal voltage is given. What we have to find? We have to find the forward bias current. So let us write the data. V is given 0.4 volt. Saturation current is given 1.17 into 10 power minus 9 ampere and the thermal voltage is given. Vt is equal to 25.2 millivolt. Okay, and we have to find I. The value of E is constant and the value of K is also constant. These two are constants, which we have already written in the previous numeric. Now, after writing the data, we need to check the units. So this is in volts, this is in ampere. We need to convert this millivolt to volt. So what is the conversion for milli? Milli always mean 10 power minus 3. So this is 10 power minus 3 volt. So let us write the formula. What is the formula? I is equal to Is exponential V by beta Vt. Why I am writing this formula here is because the thermal voltage is given and thermal voltage Vt is equal to Kt by E. That is why I have written exponential V by beta Vt minus 1. And here it is a germanium diode it is given and the ideality factor is not mentioned. So we consider beta to be equal to 1. So let us do the substitution. I will be equal to 1.17 into 10 power minus 9. This is the value of Is into exponential. What is the voltage given? 0.4 volts. So 0.4 by beta is 1. And what is Vt here? 25.2 into 10 power minus 3. So 25.2 into 10 power minus 3 minus 1. So when I take the exponential to this value 0.4 by 25.2 into 10 power minus 3 exponential, what we get here is this value I can find using the calculator and I'm going to write it directly. 7.83 into 10 power 6 minus 1. So this is the value of the exponential. Now you can minus 1 and then multiply, get the current as 9.156 into 10 power minus 3 ampere. So this is the value of current. We have to find the evaluate the forward bias current of a germanium diode. So the current flowing through the diode is given by 9.156 into 10 power minus 3 ampere. Coming to the fourth one, obtain the reverse saturation current. We have to find the saturation current. If a current of if the current at 0.2 volt means the applied voltage is 0.2 volt and the forward bias is 0.1 milliampere and the temperature is 25 degrees Celsius and the ideality factor is 1.5. So let us write the data. Current at 0.2 voltage. So voltage is 0.2 volt and I is 0.1 milliampere and the temperature is 25 degrees Celsius and the ideality factor beta is 1.5. We need to calculate Is. So the data is clear. Check for the conversions. We need to write current in ampere. Milli is 10 power minus 3. And we have to write the temperature in degree Kelvin. So this will be 25 plus 273. So this will be 298 Kelvin. 298 Kelvin is the temperature. So what we have to find is Is. I is equal to Is exponential EV by beta kT minus 1. Here we cannot neglect beta. The value of beta is given as 1.5. So let us substitute now. I is given 0.1 into 10 power minus 3 is equal to Is we have to find into exponential E, the charge of the electron 10 power minus 19 and the voltage applied is 0.2 divided by beta is 1.5. K is again Boltzmann constant 1.38 into 10 power minus 23 into temperature is 298 Kelvin. So into 298 minus 1. So whatever we have in the exponential, we can simplify using the calculator, and the value of the exponential comes out to be 179.03 minus 1. Now we need to find the value of IS. So how do we write this? IS into 179.03 minus 1 will be 178.03, and IS will be equal to what? 0.1 into 10 power minus 3 divided by 178.03. So this gives us 5.62 into 10 power minus 7 ampere. So this is the saturation current. We can also write it as 0.562 into 10 power minus 6 ampere or 0.562 microampere. Generally, the saturation current is a microampere. It is very small. So this is the saturation current. Next, find the applied voltage on a forward bias diode if the current is 1 milliampere and the reverse saturation current is 10 power minus 10. Temperature is 25 degrees Celsius and the ideality factor is 1.5. So let us write the data given. So I is given as 1 milliampere and the reverse saturation current IS is 10 power minus 10 ampere. Ampere is missing here. This should be in ampere. Temperature is 25 degrees Celsius and the ideality factor is 1.5. So let us do the conversions first. 1 milliampere will be 10 power minus 3 ampere. 25 degrees Celsius will be 25 plus 2, 73. That is 298 Kelvin. What we have to find here? The applied voltage. We have to find V. So again, we'll use the same formula. I is equal to IS exponential EV by KT minus 1. To get the answer easily or to make the simplification easy, what I do is I will write the formula for V first so that we can directly substitute and get the value. I'll write it as I by IS plus 1. IS I have brought onto this side, just transposing, it comes onto the denominator. This minus 1, when it comes here, it becomes plus 1. Exponential EV by KT. Now, we need to get the value of V. So what we do is we will take logarithm on both sides. So when we take logarithm on both sides, we have ln I by IS plus 1 is equal to EV by KT. We can substitute the values here, ln. Otherwise, I'll get the value of ln I by IS. I is what? 10 power minus 3 by 10 power minus 10 plus 1. So when we write this here, ln 10 power minus 3 and minus 10 when it goes up 10 power 7 plus 1. So I can write it as ln 1. And this value we get it as 16.11. So the value of ln 10 power minus 3 by 10 power minus 10 plus 1 is 16.11. So we can directly substitute the value here. 16.11 is equal to EV by KT. So what will be the value of V now? 16.11 into KT by E. So I'll write it as 16.11 into the value of K is 1.38 into 10 power minus 23. And the temperature we have here is 298 by 1.6 into 10 power minus 19 is the charge of the electron. You simplify, you get the voltage as 0.621 volts. So at this applied voltage, we are getting the current as 1 milliampere and the saturation current is 10 power minus 10 ampere. Coming to the next one, find the temperature at which a diode current is 2 milliampere. The diode current is given as 2 milliampere, which has a reverse saturation current of 10 power minus 9 ampere and the ideality factor is 1.4. The applied voltage is 0.6 volt. So let us write the given data. First, we will write I. I is 2 milliampere. And the saturation current IS is 10 power minus 9 ampere. And the ideality factor beta is 1.4. Applied voltage V is 0.6 volts. What we have to find here is the temperature. T we have to find. So let us do the conversion for the data. This will be 2 into 10 power minus 3 ampere. Milli we have converted into ampere. This is an ampere. This is a constant. This is in volt. Now we'll write the formula and substitute. I is equal to IS exponential EV by KT minus 1. The same way we did for V, here again we will write first the formula for T and then substitute. So I can simply write it as I by IS plus 1 is equal to exponential of EV by KT. Sorry, beta KT. We have the value of beta also. Exponential EV by beta KT. Now we take logarithm on both sides. Take logarithm on both sides. So what we get here is ln I by IS plus 1 is equal to EV by KT. So again we'll find the value of ln I by IS plus 1. So we have ln, what is the value of I? 2 into 10 power minus 3. And what is IS? 10 power minus 9 plus 1. I have 2 into minus 9. If it goes up, it will be plus 9 and minus 3. 2 into 10 power 6 plus 1. So this will be ln 2 1. So 2 into 10 power 6. So we have and this value is equal to 14.508. So let us substitute the value of ln I by IS plus 1 here. 14.508 is equal to EV by KT. So we have to find the value of T. So I take T onto this side. So we have EV by K into 14.508. So let us substitute the other values. E is constant, 1.6 into 10 power minus 19. Voltage is given, 0.6. K is also a constant, 1.38 into 10 power minus 23. And the value of ln we got as 14.508. So the temperature we are getting is around 340 Kelvin. So the temperature expressed in SI system is always in Kelvin. So the temperature, this is the temperature at which we have the current flowing through the diode as 2 milliampere. Coming to the seventh one. Consider a silicon diode with eta. So here eta or beta. I told you in some books it is given as eta. So eta or beta both mean the ideality factor is 1.2. We have to estimate the change in voltage. We have to find what? Change in voltage, that is delta V. If the current changes from 0.1 milliampere to 10 milliampere. And the thermal voltage is given here again. Vt is equal to 0.026 volts. Okay. So let us write the data first. The ideality factor beta is given 1.2. And the current is given I1 is equal to 0.1 milliampere and I2 is equal to 10 milliampere and the thermal voltage Vt is equal to 0.026 volt. We have to find delta V, that is the change in voltage. Means when the current varies means with the change in voltage. So we have to find that change in voltage where the current changes from 0.1 milliampere to 10 milliampere. So first let us write the formula. I is equal to Is exponential V by beta Vt. I am writing the formula in terms of Vt because Vt is given. And we have to write now I1. From here, we can write I1 and I2. I1 will be equal to Is exponential V1 by beta Vt minus 1. And I2 will be equal to Is into exponential V2 by beta Vt minus 1. So why we are writing this? Because the current is varying. So definitely the voltage also varies. But what we have to find here is delta. We'll take them as equations 1 and 2 and simplify them. We get V1 minus V2 will be equal to eta Vt ln. I can write it as V2 minus V1, higher minus the lower, ln I2 by I1. So this is the formula, or I can simply write it as delta V is equal to eta Vt ln I2 by I1. So beta here we are using instead of eta, we are using beta. Both are the ideality factors. So I'll write it as beta. So just substitute now. Delta V is equal to beta. Beta is given as 1.2 into Vt. The thermal voltage is given as 0.026 into ln. What is the value of I2? Is in milliampere. 10 into 10 power minus 3 ampere and this is 0.1 into 10 power minus 3 ampere. So we will write the same thing, 10 into 10 power minus 3 by 1 into 10 power minus 3. So these two will get cancelled. 0.1 this is. So delta V is equal to 1.2 into 0.026 into ln 10 by 0.1, you get ln 100. And we can get the value of ln 100 using our calculator, and that comes out to be 4.605. The value of ln 100 is 4.605. Now you simply multiply, you get delta V is equal to 0.1436 volts. So this is the change in voltage which brings out a change in current from 0.1 milliampere to 10 milliampere. Now one more problem coming to the last one. What will be the ratio of final current to initial current of a diode if the voltage of a diode changes from 0.7 volt to 872.5 millivolt and the ideality factor is 1.5 and the thermal voltage given is 0.026 volt. Okay, so what is the data given? I1 0.7 volt, I2 872.5 millivolt. Ideality factor beta is 1.5 and the thermal voltage Vt is 0.026 volt. What we have to find is the ratio of final current I2 to I1. We have to find the ratio of the current. I2 by I1 we have to find. So now we'll do the conversion also. So 872.5 millivolt, I'll write it as 872.5 into 10 power minus 3 volt, or I can simply write it as 0.8725 volt because this is also in decimal 0.7 volt and this is 0.8725 volt. So the other things are fine. So now let us write the formula. I is equal to Is exponential EV. I'll not write it as EV because the thermal voltage is given. We can write it as V upon beta Vt minus 1. Now we have to find the ratio of I2 to I1. Again from here I will write I1 as Is exponential V1 by beta Vt minus 1 and I2 will be Is into exponential V2 by beta Vt minus 1. So when we have to get I2 by I1, so I2 by I1 will be exponential delta V by eta Vt. So we have to find the ratio of the final current to initial current. I will take logarithm on both the sides. So we have ln I2 by I1 is equal to delta V by eta Vt. So first let us find the value of ln I2 by I1, then we can get the value of I2 by I1. So substituting the values of delta V. Delta V is what? This is nothing but V2 minus V1 by eta, or sorry, we are using beta here. Both mean the same. Beta Vt. So what is V2 and V1? V2 is 0.8725 minus V1 is 0.7. This divided by beta is 1.5 and Vt is 0.026. So this is the value of ln I2 by I1. And this value, if we are simplifying, what we get it as 4.423. So I2 by I1 will be equal to exponential of 4.423. So that will be 83.34. So this is the ratio of the current. So it's a number. So the ratio of final current to the initial current, that is I2 by I1, is given as 83.34. So I hope the concept of the junction diode, the calculation of the current, the saturation current and the applied voltage is very clear. So for any clarification, you can refer to this link where you have a number of numericals based on a PN junction diode. You can watch this, or you can refer to this YouTube link and solve more problems for more clarification regarding this concept. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.